Get my recording going. All right. There we go. All right, now we're ready to go. So the topic for today, and what we're going to work on pretty much all day today, is this idea of precipitation reactions. So on Monday, we began to talk about aqueous chemistry, that is chemistry in solutions. And we looked at the ideas of molarity, and just as a reminder, when you see big M or molarity, that is moles divided by liters, and that's what we're going to use when we talk about concentrations in solution. At the very end of Monday, we started to look at soluble versus insoluble compounds. If you remember that table we looked at, table, I think, 4.1. And the idea of a precipitation reaction is that you mix two solutions. And in these solutions, you have ionic compounds that are soluble. However, when you mix these, you'll create something that becomes insoluble. So here we have potassium iodide plus lead nitrate. And when they mix, one of the compounds you make is lead iodide. Lead iodide is not soluble in water. And so here's the actual experiment that's going on. We're mixing our two liquids. This yellow cloud is our solid. And the scientific term for this is a precipitant. We have made a precipitant, and this is called a precipitation reaction, where we mix two liquids and we get a solid out of it. That's the idea of a precipitation reaction. So how do we actually use precipitation reactions, or how do we handle those in chemistry? So here's our 6-step simple procedure. 1, you want to write out the formulas of the two compounds being mixed as reactants. So here we have an example where we have potassium carbonate plus nickel 2 chloride, and we're going to be mixing those together. Here, AQ, I don't know if I talked about this before yet or not, but anytime you see AQ, AQ stands for aqueous. Aqueous simply means dissolved in water. So if you're dissolved in water, and I don't know how to spell dissolved, obviously. If you're dissolved in water, you are called aqueous in chemistry. So that's what these mean. We have two compounds that are dissolved in water, and we're mixing them. And what you want to do is you just want to switch around the ions, the cations and the anions. So remember, our metals are going to be cations, so they're positive. Then we have our anions that are negative. When you have this type of problem, you just switch the cations with each other, and that will be your new products. So KCl and nickel carbonate are our new products. If you mix two gases and you get a solid, that is the same idea. And I believe your result would be called a precipitant at that point. Yeah, it's pretty much the same idea. If you mix two gases and you get a solid. Yeah. Sorry, I'm just thinking it could be called like a slightly different word that's currently like it's on the tip of my tongue, but I can't think of the name right now. But yeah, it's basically the same idea. All right. So after you write the formulas of the products, then you want to look at our solubility rules, our table. And like I said, I'll give you this table on the test on your on the sheet I'll provide to you that you have to download. So you'll have the solubility rules in front of you when you take this test, test 2. All I ask is that you know how to read that table, and we'll get some more practice for that today. But you look at your products, and if everything is soluble, if both KCl and nickel carbonate are soluble, you write no reaction. If you mix two aqueous substances together and you do not form a solid, you have done no chemistry. Nothing's happened. You did not change anything. So this is no reaction. However, if one of the compounds are insoluble, you need to write the reaction. And the compound that's insoluble gets the letter S. S means solid. All right. So moving forward with our chemistry, with this class, chemistry in general, when we are writing our equations, our molecular equations, you now have to tell me what form we are in. And I'll just write down the forms. Aqueous, dissolved in water. So that's above. S, you're solid. L, you're liquid. G, you're gas. All right. So moving forward, anytime you write a chemical equation for me, you need to tell me what state your molecule is in, or your molecule is in, because that's very important. So when we mix two aqueous things and we get a solid, we have to state our molecule is a solid. After you write the formulas, you balance the equation. Here, two potassiums, right? Two chlorides, one CO3, one CO3, one nickel. So that's balance. So if you're still having trouble with balancing, go back to our balancing discussion. Email me and I'll give you a ton of balancing example problems. There's a lot out there. But yeah, I'm just going to assume everybody can balance equations moving forward since we were tested on that and we've covered it. So I have some problems for us to actually, understand how this works. I'm going to do the first problem. I'll do A, and then I'll give you time to do B and C. So A, we have lithium iodide. So that, let me get my pen out again. This is a capital I, so that's lithium iodide, plus barium sulfate, and we're mixing those together. And we have to figure out if there's a reaction or if there's no reaction occurring. So the first thing I would do is I would write down what your products are. And remember, you do that by just switching the cations around. So when we mix these two together, our possible products are BaI2 and Li2S. And you might be asking yourself, how do I know things are twos? Like, how do I know it's Ba2? And that goes back to the idea of looking at the periodic table and figuring out what the charges of atoms are, what the charges of our metals are. If that is still confusing for you, go back to that discussion we had in the past. Again, email me and I can give you more example problems on how to determine what the charges of an atom from the periodic table. But again, we talked about that, so I'm not going to spend too much time reviewing that right now. All right, we look at our two products. We have BaI2, Li2S, and we just have to ask, are these soluble or not? So let's start with BaI2. So in our table, we say I is soluble except with Ag, Hg, Pb. So iodide, is soluble with barium. So this is a soluble molecule. So that's aqueous. Lithium sulfide. Lithium is soluble with everything. It's impossible for lithium to be paired with something and be insoluble. So lithium sulfide is aqueous. Therefore, we are not making a solid in problem A. So this is no reaction. Nothing happened. We mix two liquids together, and if we did this in a lab, they would just be two liquids. We did not make a solid. All right. So that is what I want you to do. I want you to figure out if we're going to form a solid. And if we are, I want you to write our reaction that occurs and make sure it's a balance. If we don't form a solid, write no reaction. Right? So that's where we're going to start with B and C. So I'm going to give people like 4 to 5 minutes to do this, as we're using a lot of skills here. But as always, if you have any questions while you have time to do this, please do not hesitate. As always, you can just send me a private message that no one but me can see if you want to ask questions that way. But yeah, give you all some time to work on this. When switching cations, will OH and B have a 2 after it? OH will have a 3 after it, actually. So how to determine that? So if we go to the periodic table, sodium's in the first column, so sodium's always going to have a +1 charge. Therefore, OH, to be a balance, will have a -1 charge. Iron is a transition metal, and so we do not know the charge of iron. We can't possibly look on the periodic table and determine the charge of iron. Chlorine, we can. Chlorine's a halogen. Halogens are always -1. Now, in iron with 3 chlorines, since there's -1 for each chlorine and we have 3 chlorines, overall chlorine is adding a -3 charge to our molecule. Therefore, to make this balance, that means iron was a +3. So this is iron 3 chloride, all right? So if I'm mixing iron with OH, iron is +3, like we just talked about. OH is -1. Therefore, to balance this reaction or balance this molecule, we need 3 OHs. So it'd actually be FeOH3. I did have another question if it would be Na3Cl. No. Like I said, Na is +1, Cl is -1, so it just goes NaCl. And my equation isn't balanced yet, but that is just how you make the molecules, the resulting molecules from mixing these two liquids together. And what I just worked out there from the charges, that is a skill we need to have. That is why we spent, a couple lessons talking about those ideas where we look at sodium and we know it's +1, so we can automatically figure out OH. We look at chlorine on the periodic table. We know it's -1, so therefore, if we have 3, that's -3. And then since we're making a compound that has to be neutral, so Fe has to be +3. All right, let's see if we make a solid. So OH is generally insoluble except paired with these and these. So none of those are iron. So iron is going to be a solid. So that's FeOH3 solid plus NaCl aqueous. Cl is insoluble except paired with silver, mercury, or lead. All right, now we have to balance this. And so I showed you how to do the table method. So I'm not gonna go through that whole table method right now. I'm just gonna show you the shortcut method. So we have 3 chlorines on the left side, which means we need 3 chlorines on the right side. So I'm going to put a 3 there. Now on the right side, we have 3 sodiums. So we need 3 sodiums on the left side. So we have 3 sodiums, 3 sodiums. OH, I'm just going to say that's OH. I'm not going to break it down to oxygen and hydrogen. You can, it will work that way, but I'm just going to say 3 hydroxides on the left, 3 hydroxides on the right, that's balanced. 1 iron on the left, 1 iron on the right, that's balanced. So that's your equation. 3 sodium hydroxide aqueous plus iron 3 chloride aqueous will make iron 3 hydroxide solid plus 3 molecules of sodium chloride aqueous. So let's see here. Do we only balance the equation when we have an insoluble? Yeah, so if you don't have something that's a solid, you write no reaction because nothing happens. Only balance equations when you have a solid, because that's the only time chemistry is happening, right? Do you have to write Fe and Roman numeral 3? No, the Roman numeral 3 is only when you're naming it, right? So if I was going to name this, I would write iron 3 chloride. However, that's the only time this is used. When writing the molecule, you'll never put a 3 there, because writing a 3 would mean you have 3 atoms of iron. We only have 1 atom of iron and has a charge of +3, right? So if I was going to rewrite this without any of my notations, just so we have that in front of us, NaOH aqueous plus iron 3 chloride aqueous makes iron 3 hydroxide solid plus 3 molecules of sodium chloride aqueous. That's your answer. You don't need any of the charges above like I wrote. Oh, sorry, I've got the balance. 3. There we go. So you don't need any of the charges above your molecules like I have down here. That's just for like making sure you have the equation right. And that's for just checking yourself. The actual answer would be that though. Okay. I thought you couldn't add subscripts to balancing equations. I'm referring to OH3. You can't. That's correct. You cannot add subscripts, but I'm not balancing, I'm not adding a subscript to balance an equation. I'm just making a new molecule, right? So in the reaction, if iron has a +3 charge, hydroxide has a -1 charge, that means I need 3 hydroxides, 3 OHs to balance out that +3 charge from iron. So the molecule it forms is iron 3 hydroxide. So I have 1 iron in the middle and 3 hydroxides bound to it. So I'm not changing the subscript to balance equations. I'm putting that subscript there to tell you what the molecule is. And that has to do with charge, right? What I can't do, for example, like if I have NaOH, that's balanced. The balance by charge. I can't put a 3 after the Na here because now that's a charge imbalance. My molecules have to be neutral. No, it's a good question. So don't ever be sorry for asking a question. How do you know which compound goes first when writing products? Always put your cation first and then your anion. If you're asking which one comes first, iron hydroxide or sodium chloride, that does not matter one bit. You could write sodium chloride plus iron hydroxide. All right, so let's do C now. So we have lithium bromide plus potassium hydroxide. So again, let's rewrite our molecules, and I'm going to change out of this purple pen. Let's go to a good black pen. I guess that's not quite purple, but whatever. So we have lithium bromide plus potassium hydroxide. The first thing we want to do, like I said, is just switch the cations around to see what we make. So we would make lithium hydroxide and potassium bromide. And those are balanced electronically. That is, they're neutral compounds. Bromine's -1, lithium's +1, hydroxide is -1, potassium's +1. So we don't have to do anything with subscripts here. Lithium hydroxide. Lithium, it's soluble with everything, so that's aqueous. Potassium bromide. Bromide is soluble except with silver, mercury, and lead. Potassium's not one of those. Aqueous, no reaction. I did not form a solid, therefore, no reaction actually happened. Questions about the idea of precipitation reactions. There we go. I have to think about its name. All right, so let me clear. Well, here's a question. Well, we have table 4.1. Yes. All I ask is that you know how to read table 4.1. Reading tables is a very important skill for life, so I want to make sure we have that. So you don't need to memorize it. You don't need to memorize this for me. I will give that to you. All right, clear all my scribblings. The next thing we're going to talk about is how to write aqueous reactions. And there's a couple different ways we can write it. One, the way we've been doing it this whole time. When's our next test? I have to look at the syllabus. I don't have that information off the top of my head. One way to write it is what we've been using via the molecular equation. All right. The molecular equation, we should all know. We just write our molecules out with our state symbols. The next way is a new way that we haven't looked at before. It's called the complete ionic equation. In the complete ionic equation, you take anything that is aqueous and you split it into ions, right? So some things to note. When you write the complete ionic equation, you not only have to write the state it's in, you have to write the charge. So in an ion, ions are not neutral like we talked about. So when you write ions, you have to write the charge. Subscripts like NO3, 2, they will now go in front. So you have two molecules of NO3 negatively charged and it's aqueous. Numbers out in front, we have to distribute. 2 potassium, 2 chlorine. Anything that's solid, you do not break up because it's a solid. You only break up aqueous compounds. So solids stay together, and then you break up your ions. So that's the complete ionic equation. The net ionic equation is you see what ions are the same on both sides. I already highlighted those with a blue line through them. Any ion that is the same on both sides of the equation, they get canceled out. They actually don't do any chemistry. They are what's called spectator ions. That is, they just watch the chemistry happen without actually being involved in the chemistry. And honestly, when we get to the net ionic equation, we don't care about spectators. We only care about the molecules doing the chemistry. So they get canceled out. And your net ionic equation is just whatever is left from not being canceled out. And it's what's actually doing the chemistry. So our equation is lead plus 2 chlorines make lead chloride. That's our equation. All right, so any questions about that idea? Molecular equations, complete ionic equations, or net ionic equations? Why isn't oxygen on the reactants charge 6? I'm not sure I understand the question. Charge 6. Why would it be charge 6, right? NO3 is a ionic it's a polyatomic compound. So that sticks together. You never break up polyatomic compounds. Remember that table we looked at? You never break that up. NO3 is one of those. NO3 is being paired with potassium. If we look on the periodic table, potassium's in the first column, so potassium has a +1 charge. Therefore, NO3 has a -1 charge. Can you re-explain complete? Complete is you look at your molecular equation, and anything that's aqueous, you break apart, right? And you break apart into ions. So you break apart your cations and anions. You write the charge of your cation and your anion, and you write the symbol, the state symbol, aqueous, solid, and all that. If it's solid, you do not break it apart. Since you distribute the 2 for NO3, I did. The 2 is distributed. It's in front of it, right? So 2 NO3. Where can I go to do more practice for net ionic equations? So we will do practice today. Then, if you would like more practice, I ask you email me, and I can get you resources. What makes a solid compound? Solid compounds are determined from table 4.1. So I know it's hard to see through all my writing, but that's what makes a solid compound, these solubility rules. All right. So I think the best way to understand anything in life is to do it with your own hands, right? So let's try that now. So let me get rid of all my scribbles. All right. So we need to write a balanced, complete ionic and net ionic equation for each reaction. So I'll do A, just to give you another example. Then I'll give you some time to do B. All right. So first, let's see if this reaction's balanced. 1 magnesium, 1 magnesium. 1 sulfur, 1 sulfur. 1 copper, 1 copper. 2 chlorines, 2 chlorines. That's a balanced reaction. Everything's the same on each side of the equation. All right, now I need to write my complete. So for complete, anything that's aqueous, you separate. So magnesium, if we look on the periodic table, magnesium's in the second column, so it gets a +2 charge. Then I have to rewrite the aqueous. And the reason why you're breaking this apart, let me actually talk about the reason, right? Anything that's aqueous means like it's actually, for an ionic compound, they're actually not together in solution. They're separated by water to form the ions. And we talked about that on Monday. We are making electrolytes. That's what the aqueous means for ionic compounds. So that's why we're breaking them apart here. So magnesium 2 plus aqueous, sulfur 2 minus aqueous. How do I know it's 2 minus? 1, it's paired with magnesium, and there's only 1 copy. Magnesium's always 2 plus, so to be a neutral compound, sulfur has to be 2 minus. The other way I know is that on your periodic table, sulfur is right below oxygen, and those two molecules are like almost always -2. All right. Copper. Now, copper is a transition metal. I do not know its charge from the periodic table. I know its charge from being paired with chlorine. Chlorine is -1 always because it's a halogen. I have 2 chlorines and only 1 copper, so copper has to be +2 to make a balanced reaction. +2 -2 is 0. So that is a neutral compound. So copper is +2, aqueous, plus, now I have 2 molecules of chlorine minus aqueous. All right, common mistake I see on these. I'm sure many of you are going to be tempted to write Cl2 aqueous. That is incorrect, right? Halogens, F, Cl, Br, I. They are always single if they're aqueous. If they're aqueous, it's only 1 F, 1 Cl, 1 Br, 1 I. You're never going to have Cl2 aqueous, Br2 aqueous. That doesn't happen. So it's 2 Cl minus. So any halogen will always be by itself. What is that going to make? Copper sulfide's a solid, so we don't break that up. Magnesium, 2 plus, aqueous, plus 2 Cl minus, aqueous. That is my complete. Now my net is I look what's the same on each side of the equation. So I have magnesium. Let me change my pens now. Let's undo that. So I have magnesium 2 plus on one side, magnesium 2 plus on the other side. They cancel out. I have chlorine, 2 chlorine minus on one side, 2 chlorine minus on the other side. They cancel out. So my net equation is copper 2 plus, aqueous, plus sulfur, 2 minus, aqueous. Make copper sulfide solid. Now you might be asking yourself, why did I put copper first? Personal preference. Usually cations are first, then anions. It doesn't matter. If you were to put sulfur plus copper makes copper sulfide, that's completely fine with me. All right, so see if you can follow that logic and do B. So I'll give everybody a few minutes for that. If you have questions, get stuck somewhere, let me know and I'll see if I can help out. But yeah, let's do that right now. So do we need to balance B before we do anything? I would, it will just make your life easier if you balance it when it's in the molecular form. So I would suggest that, yes. Tess, would you give us a complete and ask us to turn it back into a molecular equation? Ooh, that is interesting. Wish I would have thought about that, but nope. I do not ask you a question like that during class, so I'm not going to ask you a question like that on the test. Anything we go over in class will be on the test, but I will not ask you stuff we didn't go over. Although that is a skill I would expect people to have if you do this. I'm not going to test you on that. All right, so had some time to work on this, I hope. Just as a reminder that this time is to be working on problems. So if you're not, then it's not the best use of your time. All right, so complete. Take our molecules and break it apart. So I have potassium 2, K2. So I have 2 potassiums that are solid. Like my aqueous or my halogens, my metals are never going to be found in any like together. That's like any metal. Any metal is always going to be by itself. So if you see something like K2, K2 is not a molecule. If it's a metal, you can only have one copy of it. So you need to put the 2 in front. So 2K plus, and if we have 2 potassiums and aqueous, and if we have 2 potassiums and 1 SO4, that means the SO4 had a -2 charge to balance out the charges. So SO4 -2 aqueous. That will make calcium, or that plus calcium 2 plus aqueous. Plus, again, 2I minus aqueous for the reasons we talked about above. That will go and make calcium sulfate solid. So it's a solid, I don't break that apart. Plus potassium iodide. Aqueous, sorry, got a little ahead of myself there, aqueous. Now this isn't balanced, and I should have balanced it before. To balance it, you just put a 2 in the potassium in your iodide. So you need a 2 here. Let me make a little bit of space here. So yeah, so no more eraser, please. Thank you. Plus 2I minus aqueous. So that's our balance equation. Now we have to do the net. So we just look to see what's the same on both sides. So we have 2 potassiums on each side, they cancel out. We have 2 iodides on each side, they cancel out. So what we're left for as our net equation is we have calcium 2 plus aqueous plus SO4 2 minus or -2 aqueous will make calcium SO4 solid. That's our net equation. Questions about complete ionic equations, net ionic equations, or anything from today? Can I explain why I wrote potassium like that? So, like I said, any metal, be it potassium, sodium, iron, calcium, anything that's classified a metal on the periodic table, when it's in water, if it's in an aqueous compound, it will always be by itself. So you can't have K2, you can't have Ca3, you can't have any of those in an aqueous component by itself, because that doesn't happen in reality. So what happens is that if you have K2SO4, that's my rough drawing of K2SO4, and you put that in water, each potassium will float away by itself, and the SO4 will float away by itself, right? So the potassiums aren't attached. And so that's why we write 2 potassium, right? If you write K2, what you're saying, K2 means your potassiums are bounded to each other. A metal will never bind to itself in water. A metal will always be by itself in an aqueous compound. So we always have to write like potassium, calcium by itself in an aqueous compound. Can you please leave right there for a second? I will leave everything written right there. Forgot about not breaking up solids. Yep, so if it's a solid, it does not come apart. Why wouldn't you put the 4 in front of SO4? Because SO4, if you remember from, I don't know, 3 weeks ago, I want to say we talked about this, is what's called a polyatomic ion, right? It's a ion made out of multiple nonmetals. The bonds between the sulfur and the oxygen are covalent. These are covalent bonds, so they don't break apart. Covalent bonds never break apart in water. They're too strong, right? So SO4 is a molecule with 1 sulfur and 4 oxygens. So if I put that in water, I'm not breaking covalent bonds, so it's still 1 sulfur and 4 oxygens. That's why you don't put like a 4 and make 4SO, because that's not the molecule. The molecule is SO4. And to really understand that, you have to understand the idea of polyatomic ions. You have to understand the idea of ionic molecules, molecules that have an ionic bond, versus molecular molecules, molecules that have a covalent bond. So that's, like I said, that's going back to 2 to 3 weeks ago. So if that's still confusing to you, definitely go and recheck out those slides, rewatch the lecture video, redo the problems. And if something's still confusing, shoot me an email and we can work on it together. Any other questions? If not, that's all the time we have. So we got through about half. Yeah. So we'll continue this idea of molecular, ionic, and complete equations on Friday, but in the terms of acid and base reactions. So we'll do that for like the first half of Friday, and then we'll move on to something new. But otherwise, as always, I'll put this video up. If you have any questions, want more help, want more problems, all you need to do is email me and I will get back to you with that. I'll put homework up as always, due Sunday. Other than that, have a good rest of your Wednesday, everybody.